In the last video, we talked about functions and we talked about variables, which I recommend that you watch the previous videos. Now, in this video, we're about to give our code something every intelligent system needs, which is the ability to think before it acts. And these are called conditional statements. So let's start with a simple example. First, let's create a variable, and we're going to call it temperature. Okay? And then we're going to give it a value of 35. Right? So then we're going to tell the computer to create some kind of a condition. Let's say, for example, if that temperature that we have is greater than 30, then I need a message to be displayed that says temperature is hot. Okay? And then if the temperature is not greater than 30, else, or anything else besides above, like if it's not above 30, if it's below 30, for example, then I want you to print temperature is not hot. Okay? So here I'm just telling the computer if the temperature is greater than 30, just say it's hot, otherwise say it's not hot. So let's save this and then let's run it. Here we go. So the message we get, temperature is hot. Why? Because the variable temperature is 35. We are saying that if that variable is greater than 30, then a print is hot. If it's not, then it send a message that temperature is not hot. When we run this, you're not just printing text. You're making a decision. This is the first time your code looks at the world, evaluates something, and chooses what to do. This single line, if temperature is greater than 30, is like a doorway. It's how we teach machines to reason. In Python, the decision words are that we use are if, which is where we're using it on the first condition, and then else, and then we have something called elif, something like that. Elif, which we're going to use it a lot in our examples. These kind of conditions, we use that in real life. If I say, if it's raining today, I will take an umbrella. Otherwise, I will go outside. And that's not programming, that's logic. And you already do it every day. Python writes it down, and that's the only thing. We just write it in a different language, but we use it in our own language. So now let's take that idea, the power to decide, and bring it into a real system. So next, we will imagine this temperature value isn't just a number. It's coming from a sensor. And that means our decisions will start to control hardware. All right, imagine this value doesn't come from me typing 35. It's coming from a sensor, maybe inside a drone or a piece of medical device or equipment. So instead of writing a fixed number, let's simulate a reading. Let's just remove this example that we did. We're going to do something similar to that. We're going to use the same principles, except now we're going to simulate a reading, a sensor reading. So let's just remove this. And in order to simulate something, we need to use random module. So random module is basically a Python module, a Python library, or module, where it has multiple functions inside this library, where you can pull those using the import random. It doesn't give true randomness. It's like a deterministic pseudo-random sequence. It has its own formula in the back end, but it's perfect for simulating unpredictable sensor values, just like this example that we are doing. So if I go to the next step, instead of me calling temperature equal 35, let's say, this time what I'm going to do is I want to simulate something. I'm going to call random, and I'm going to tell random to just create some random numbers for me. So I will use the basically from that library, I'm going to use this one, rand integer, and then I will create value between 20 and 100. So here, basically, random integer or int 20 to 100 returns an integer between 20 and 100. Think of that as a plausible temperature range from a device. I'm storing it in what? In the variable temperature. So the rest of the code can use it like a real sensor reading, okay? So now every time we execute this code, is going to create a different temperature value using the random module, okay? So how we do that? Well, let's just print the same as before. Let's say sensor reading, okay? And then we're just going to call the temperature value, okay? This is just to give us the message and show us what exactly the value that we are reading currently, okay? Just a quick print to observe what our sensor delivered this time. Every execution, as I said, will likely see a different value. Now, each time the code runs, I'll get a different temperature, just like a real device in motion, okay? Let's just bring our condition or our decision logic back, which is what? Which is the if statement. If temperature, okay, is greater than, let's say 70 this time, I want you to print me a message that says, hello, like what temperature is really high and I need temperature, high temperature and turning on fan, okay? And then what if it's not above 70? Or let's just make it a little bit exciting and just make it equal to 70. So now if it's equal or above 70, then print high temperature and I want you to turn on the fan. Otherwise, if it's not greater or equal to 70, like let's say 69, 68, 67, then print sorry, here, temperature is normal, and then I would just say turning or like turn off fan, okay? Or you can just say fan off, just like that. All right, keep it simple. So if the part where if temperature is greater than 70 is the rule. Above 70 degrees, we treat it as it's hot. Thresholds like this come from, let's say, requirements or testing. Inside the block, we print the action, turn the fan on. Else covers everything not greater or equal to 70, which is normal operation, fan is off. Let's actually run it and then see the result. I'm going to run it a few times to show you the randomness of the temperature. Right now, temperature is reading 49. So what? Is it greater or equal to 70? Fan is off. All right. So, because it's not. Let's run it again. 97. Is it greater than 70? Of course. So turn the fan on. Let's do it again. 51. Fan off. So, look at that. Every run gives a new result. If it's above 70, fan on, or equal to 70. Otherwise, turn it off. This is the core of how embedded systems make decisions. When you are flying a drone, the same kind of logic checks if the battery is too low. When you are driving an electric vehicle, it decides when to engage cooling or reduce power. So every if statement you write here could exist inside a machine that protects hardware, data, or even people. In production, we don't hard code ranges like from 20 to 100. We read from actual sensors, debounce noisy signals, and log events. We also replace prints with a control command, like toggling a GPIO pin to drive, let's say, the fan relay. That's where we are heading next. Let's take this one level deeper. In the real world, we don't just have one sensors. We have many sensors in a system, let's say. Temperature, we have current, we could have voltage, vibration, and they're all talking at once. So what happens when two things must be true at the same time? So we're going to remove this and keep the temperature sensor, and maybe same idea in terms of the temperature sensor, But now I'm going to add a new reading called current. And then I will give a value to it and also a random value. But instead of me this time using rand integer, I'm going to use the uniform, which is going to give us some decimal numbers instead of only integer numbers, because current can be a decimal number, maybe 1.8 amps or maybe 2.4 amps, things like that. So, and it's going to be between 0 and let's say 3.0. Okay. So now our system is watching both heat and electrical load. So now we're going to build the logic similar to what we did before. So we're going to start with temperature. If temperature is greater than 70 and current, I didn't say or, I said and the same time current is 2.0, then I want you to print me, let's say, overload detected, and I will say shutting system. Or I would say like this, system shutting down. Okay? Now, the next condition, elif, okay? Temperature is greater than 70, then just turn on the fan. That's it. So we can say overheat and fan on. And lastly, anything else, then just print system stable. That's it. Okay, so if temperature is greater than 70 and current is greater than 2.0, this means both conditions must be true at once. If it's hot and drawing too much current, we should shut down the system. If only the temperature is high, we just turn the fan on. Otherwise, everything is stable and normal. Now, let's run the code and see what happened. We're going to clear this, save this, and let's just run the terminal. All right. So what do we have? System is stable. I can run it again. And because we are giving values, random values, fan on. So that means what? That means it's giving me something, and it's basically, that means the condition here is working. Why? Because temperature is greater than 70, but that's it. So the current, it's still less than 2.0. So if I run it again, it's giving me system is stable. Why? Is because it's not greater than 70 and it's not greater than 2.0, and it's not only greater than 70. So our code doesn't just react, it cross-checks. It's reasoning. It's saying don't panic unless both warnings light up. And that's how real embedded logic avoids false alarms. This kind of logic runs inside drones, power systems, even spacecrafts. It's called conditional logic fusion, combining multiple signals before deciding what to do. We've gone from a single if statement to a real decision chain that could control a fan, a relay, or even a full safety cutoff. But we're just getting started. In the next section, we will take this same code and turn it into a system that monitors, decides, and recovers automatically, just like a professional embedded controller. Now that we can detect both temperature and current, let's make our system a little bit smarter. In real embedded devices, you never want your fan to keep switching on and off rapidly. That's called relay chatter. So engineers use something called hysteresis, basically a small cushion between on and off. So let's see how it works. What is hysteresis and how it works using the temperature example that we are doing. So imagine you're controlling the fan with a temperature sensor, and if you set it to turn on exactly at 70 degrees Celsius, let's say, and off at the same point. So you turn it on and off at the same point. You have one threshold, and that is 70 degrees Celsius. what happened is the fan will keep flickering on and off every few seconds. And the reason is because temperature naturally fluctuates. It doesn't stay on the same degree. And that's going to create a problem, which is the relay chatter. So to stop that, we add the hysteresis, which is a small buffer zone between two limits. For example, the fan turns on when it goes above 70 degrees, and then it turns off only when it drops below 60 degrees. So now you have what? You have the 10-degree gap, and that's the hysteresis zone. So the 10-degree gap is the hysteresis zone. It's what keeps the system stable and smooth. No more of these. If the degree, let's say, went to 71 degree, if the degree went to 61 or 62 or 63, 65, it's not going to change until it reaches, or the fan will not turn on until the degree goes above 70. So there's enough time to switch from on and off. And that's what hysteresis is. So let's start from scratch so we can build this example, and we build this control loop step by step. Okay, first we're going to start, let's remove what we have. Okay, so first, as always, we're going to start by writing import random. So here, as I mentioned, random is going to help us simulate changing temperature readings so that the numbers move like real sensor data. And then we're going to import time. Okay, so time will let us slow the loop down a little so we can actually watch what's happening between each update. So next, we're going to go by creating a variable called fan on, and we will give it false. So I'm setting it to false, which means the fan is currently off. Think of this like the real state of a fan relay is just sitting there waiting for a command, okay? Now I'm adding two temperature limits, the max temperature, which is the point where we want to turn the fan on. So that's going to be 70 degrees. And then the minimum temperature, and that's the one when we want to turn it off, which is going to be 60 degrees. Okay, so this 10-degree gap is the hysteresis range. It's the little cushion that we talked about that prevents the fan from flipping on and off every few seconds and causing some relay chatter, for example. Okay, so next I'm going to start by creating a for loop that runs 10 times. So the way it's going to be done, for, and you can imagine this like 10 sensor updates happening over time. Each loop is one new reading from the temperature sensor. Okay, so we're going to say for I in range of 10, which is 10 times. Okay, and I'm going to call the temperature is equal. Here I'm just going to create basically the temperature sensor, and I'm gonna use the random module here, dot rand integer, and then I'll give between 50 to 80 to generate a random temperature between 50 and 80 degrees. Okay, so something is wrong here that I did, because I said for I range, so it should be for I in range. See? So that's our fake sensor reading, I would call it, constantly changing, just like it would be in real devices. Okay, then we're just going to print the data that is coming from the sensor. So this line basically that I'm going to do to print what's going on, what's happening. So I'm going to say f, just to kind of make it fancy. We're going to call the number of cycle and I plus 1. So here I'm just saying I plus 1, which it makes it start from 1, because when we say for I in range 10, I'm going to start from 0 to 9. So I want to make sure that it's 10 times. So I want to start from 1 instead of 0. And then I'll just say temperature equal temperature. So it prints the value in Celsius. Okay, so this line just prints what's going on. I'm going to show the cycle number I plus 1, which I plus 1 makes it start from 1, as I mentioned, and the temperature. So the little f that I just mentioned here before the little f here that I mentioned before the quotes means that it's an f string, which lets me mix variables and text easily. Just I did like temperature, that's a text, and then I'm adding variables with the brackets. You got to make sure that you have the brackets, and then you can add those variables that you want to add. Okay. All right. So here comes our first condition that we're going to add. So what we're going to do is if temperature is greater than maximum temperature and not fan on, then fan on is going to be equal to true, and I want you to print fan turned on. So what happened here, if the temperature goes above 70 degrees and the fan is not already running, then we turn it on, and that's what the not fan on part checks. Okay, so the one here that I mentioned. Okay, so these two conditions needs to meet together because I'm mentioning the and condition. It makes sure we only, like the not fan on, it makes sure that we only send the turn on signal once. So imagine if the condition is right, but the fan is already on. If the temperature goes above the maximum temperature, but the fan is already on, we don't need to turn it on again or request to be turned on again. So it's important to have these two conditions together. Then we're going to print it out. What are we going to say? Fan turned on. Next, we're going to give the other condition, and we're going to use elif temperature less than the minimum temperature and fan is on, not off. Then in this case, fan on is going to be what? Is going to be false. And then I want you to print fan turned off. So what happened here is the opposite case. If the temperature drops below 60 degrees and the fan is currently on, then we shut it off. Notice how the fan here, the fan doesn't turn off the moment it dips below 70. It waits until it's really cooled down, and then it would turn it off. And that's the beauty of hysteresis. The last condition here is else. Else here, I'm saying if none of these conditions would happen, or if neither condition is true, meaning we are somewhere between 60 and 70 degrees, then in this case, we just print no change, and we say system is, or system stable. And that's it. So here, that tells us that the system is holding steady, no unnecessary switching. And then finally, we add a short half here that says time sleep 0.5. So here I'm adding a short half-second pause. It's like the heartbeat of the system, giving it time between readings so you can actually see the logic plays out in real time. Let's run the code and see exactly what we just built. So let's run it. All right, here we go. Check this out. So we have cycle 1 through 10. So that's success. The for loop reads from 1 through 10, or from 0 through 9. So you have 10 cycles. And that's the reason I said I plus 1, because I want to start from cycle 1. I don't want to say cycle. If I didn't mention here the I plus 1, it'll start cycle 0 through cycle 9. It's fine, but I want to keep things and stay on the same page on this. So then the temperature is equal 75. Is it above 70? Yes, then turn on the fan. Okay, it's 57. Is it below 60? Then turn it off. Okay, now what do we have? 61, 64. Is this between 70 and 60? Yes, and that is in the buffer zone. So then in this case, if it's in the buffer zone, no change. System is stable. This is great because what we just did right now, we just built the hysteresis, the simple trick that keeps real machines from constantly clicking, overheating, or wearing out. And just like that, we just build our first intelligent control loop, a tiny piece of logic that thinks before it acts. Every cycle, the logic rewrites its own boundaries. It's not just reacting anymore, it's evolving, as you can see. This is exactly how real embedded AI controllers stabilize aircraft, you have prosthetic limbs, or even satellites, by continuously turning themselves against reality. Notice how we didn't need a neural network to get adaptive behavior. This is pure conditional logic, but used smartly. True intelligence isn't just in algorithms, it's in how you let your system change itself safely. So when we talk about AI in embedded systems, it often starts like this. If it keeps overheating, lower the threshold. If it stays too cold, relax it. If the sensor fails twice, enter diagnostic mode. That's adaptive logic, the same principle behind predictive cooling, flight control, and smart home automation. Now our machine can do three things: think, protect itself, and adapt. And the final thing that we're going to mention, we will connect this to something even more powerful: learning from history, turning conditional logic into predictive behavior. Everything we built so far, every if, elif, and else, is more than a syntax. It's a blueprint for intelligence, because when a machine can decide, protect itself, and adapt, the next step is clear. It learns to predict. In real embedded AI like drones, prosthetics, or even brain-machine interfaces, the system watches patterns over time. It starts asking, what usually happens after this? Can I act before it happens? That's foresight, and it starts with the humble if. Now imagine the system doesn't react to one reading. Imagine that it remembers the last few, maybe the last 10, and it looks for patterns. This, what we're going to do. We can just add something here. Now, just for the sake of the example, we're not going to actually predict something, but one thing we can say is like, we can create some average, let's say last 10 readings, and then it'll be like some predicted variable. And then here we're going to say if the temperature, okay, is greater than the average, the one that we created, then I want you to print that predicted, like this, predicted rising trend. All I'm trying to say here, we can say the predicted rising trend, and then just activating cooling early. So what is this here? We're basically trying to see that single condition turns reaction into prediction, okay? So this line says if the current temperature is higher than the recent average temperature, or the recent average last 10 readings, I want you to activate cooling early before things gets too hot. If I have last 10 readings that are showing some kind of a pattern, then I want you to turn on the cooling earlier than it should be. Condition turns reaction into prediction. Now the system isn't just responding, it's anticipating. And that's the same logic behind early warning systems, flight controllers, and even the predictive circuits in your brain. And if you want to run this actually, and you add, let's say, for example, 65 here, you can still see some reading, because all I have to do is save this and run it. and it's going to give me 10 readings. And here, look, no change, system stable. And then after that, predicted rising trend, activating cooling early. Okay. So when people say AI is complicated, remember, it all starts here. One comparison, one decision, one conditional statement that quietly asks, if this happens, what should I do? This is the essence of every thinking system, from thermostats to rockets, from neural implants to spacecraft autonomy. Every intelligent machine is just a network of decisions, each one born from a single if. So next time you write if temperature is greater than 30, remember, you're not just programming a rule, you are building the foundation of reasoning, the same logic that drives the systems shaping our future. Because every great intelligence, human or machine, begins with one simple question. What happens if? If you got a value from this video, give it a thumbs up and subscribe to the channel. Take care, everybody. Bye-bye. Bye-bye.